So this last unit, the last unit of the year, and it bums me hard that we're not going to be together for this. We'll try to make the most of it. But electricity and magnetism, twin properties, super important, super fundamental, super fascinating, mysterious kind of. There's all kinds of quantum things going on with these tiny moving charges and moving particles and electrical magnetic type of stuff. So I'll try to do it justice. Um, this first chapter deals with static electricity, the study of which is electrostatics. The word static means at rest, so electricity at rest is really kind of an oxymoron. Um, it's kind of, well, never mind. I had a sarcastic joke I was going to use. Um, but more specifically, it's the study of electric charges and forces that they produce and their behavior in and on materials. You're familiar with static electricity in the form of lightning. You're familiar with it when your socks cling to your pants as you uh, pull them out of the dryer, or if you pull two polyester blankets apart, you hear all kinds of clicking and static charges when you comb your hair on a really dry day. You might get dry flyaways. That's static electricity. Okay, so static electricity is all around us. Static sparks are basically a miniature version of this big version, super big version, little tiny version. Okay, the buildup of charge and a difference in that buildup, and then you get a discharge. Okay, static cling, when you have socks that cling together. In the very nature of matter, what holds matter together? Electrostatic attraction. Okay, so we have positive and negative particles. That electrostatic attraction and the bonding in covalent and ionic bonding is what holds matter together. Um, Electrical appliances, the electron age, way back at the turn of the last century, had all these wonderful electrical appliances. This was high tech for their day. In fact, the rural electrification was driven by the desire for everybody to have refrigerators, not the light bulb, a little known fact in history. Okay, so I think instead of being called the information age, this should be called the electronic age because we've really learned how to use and manipulate and get the most out of electrons and how they work and electricity and electric charge. So, all the little fun toys and tools that we have um, all use static electricity in various ways. Okay, so electric forces and charges. Um, Unlike gravitation, electric forces have attractive properties as well as repulsive properties. They can attract and repel. Um, so gravity can only attract, whereas electrical can attract and repel. Um, it's one of four fundamental forces in nature. See if you can think of the four. Pause the video if you have to. The strongest force in nature, not surprisingly, is called the strong force. It's the force that holds matter together, the force that holds the protons and neutrons together in the nucleus of the atom. The second strongest force in nature is the weak force. Kind of a dumb name, but it's weak relative to the strong force, but it's stronger than the other two, which are electromagnetism and then the weakest force in nature, kind of surprisingly, is gravitation. It takes things the size of planets to have significant enough gravity to talk about it and measure it significantly. So the fundamental force is electromagnetism is billions of billions times stronger than gravity. If you look at the gravitation constant, the value of it is like 10 to the negative 11th, and electromagnetism, the value of it is 10 to the positive 12th, I think. So billions of billions, meaning it's a billion times stronger than gravity. Um, the fundamental property that causes these forces is charge. So electric charge causes electric forces. Positive charges have a force in repulsive force, and negative charges have an attractive force. Okay. Like charges repel. So two positive charges pushed near each other will repel each other. Two negative charges pushed toward each other will repel each other, but opposites attract. A positive will attract a negative. Okay, and if we draw the field lines, we can see positive, positive, and the force fields are repelling each other, keeping these two particles, positively charged particles, repellent. And then the force field drawing over here is similar to this one up here. Force of attraction, positive or negative. Okay, conservation of charge. Electrons and protons have charge. Neutral atoms have no net charge, meaning the positive and negatives have to cancel out, so the number of protons and number of electrons are equal. Ions have charges, so they have a surplus of electrons or a deficit of electrons, and it's the electrons that are conferred and transferred because the protons are buried deep within the nucleus. So when something becomes quote unquote positively charged, what's happening is that it's losing electrons, not gaining protons. And that's even true when you have an object like in the lab we're going to view, a glass tube that is being rubbed with a piece of cloth. The cloth is removing electrons from the glass because it has a stronger attraction for electrons. So the glass becomes positively charged. Okay, so that's what I just talked about. Objects can be conferred with charge as well. Think of a dry day and you're walking across carpet and you scuff your feet as you walk, and just the rubbing of your feet, and then you touch a doorknob, and so you convert a charge from the carpet. Okay, so here's the essence of the lab that you're going to view. Unfortunately, we can't do this, although you can do it on your own with stuff in your house. So we're going to be conferring charge from one object to another by the gain or loss of electrons, not the gain or loss of protons. And then we'll look at the behavior of what's happening. So conservation of electrons. Electrons can neither be created nor destroyed because particles can neither be created nor destroyed. They can simply be transferred from one object to another. Okay. So if we look at the electrical equation as compared to the gravitational equation, we see the force and the force of electrical interaction and the force of gravitational interaction. K is the electrical constant, G is the gravitational constant, Q is the charge, M is the mass, D is the distance, D is the distance. So you can see the general form of them are strikingly similar. A couple of differences is the charge and then the constants. So if you look at the value, Q is the charge, K is the constant of proportionality. Oh, I was wrong. It's 10 to the 9th, not 10 to the 12th. And so you can see there's 10 to the 20th difference between the gravitation constant and the electrical constant. Okay. Then lastly, on this first section, conductors versus insulators. Conductors, we think of things that transfer energy easily. It's because they have loose electrons. So things like metal have loose electrons, so the charge can be transferred readily. Whereas insulators, they don't stop the movement of charge, they just slow it or impede it, or it's difficult to transfer charge through insulators, largely because they don't have loose electrons. So the electrons are more tightly held, so it's more difficult to transfer charge. Now, conversely, there are semiconductors, materials that can either conduct, or insulate. And we've learned how to kind of convince them to be part conductor and part insulator. So things like semiconductors, um, materials like silicon and germanium and gallium, all those that are lined up in the semi-metal section of the periodic table, they can be used to make microcircuits, which are essentially lines of atoms that are the conductors, and then lines on either side of atoms that are the insulators. And then kind of the brave new world is there are superconductors, things that conduct with little or no resistance. The problem is the only superconductors that we have exist at very low temperatures. Okay, although recently they have had a high temperature superconductor, and by high temperature, it's relative. 100 Kelvin, which is negative 173 degrees Celsius. So it has to be cooled with liquid nitrogen, but it is a superconductor and it's a reasonably warm temperature. So normal temperature superconductors are potentially possible. Graphene made of just ordinary carbon, graphite, is a possibility. So kind of check for new discoveries. Okay, so that's it for the first intro to static electricity.